Greetings, chemistry students on a cold day. Here is your alternative to being in class. These are things that would have otherwise been used together on the next class day, but let's switch and do today what could have been Friday. We're going to talk about, on this recording, the acidity of alcohols and phenols a little bit. We've already talked about identifying an ether, but we will do some more about distinguishing between ethers and alcohols. We'll talk about thiols, which are sulfur compounds, and the reactions of thiols, converting them into disulfides or taking them apart. That is the goal for this recording. Now, to talk about the acidity of alcohols and phenols, first we have to remember what in the world is an acid, because we haven't talked about that for a little while. Some of you might recall from another course, the simplest definition we'd like to use in this course is that an acid is a proton donor. Anything that can provide H+ in a water solution is considered an acid for our purposes. So in terms of alcohols and phenols, they're only very weakly acidic. Only very weak. And that means that if you're looking at the alcohol as shown at the bottom of the screen here, the alcohol has the ability to lose a hydrogen ion, and the hydrogen ion is picked up by water, making hydronium, and an anion results. In this case, for ethanol, you would get an ethoxide ion. But notice the arrow is significantly only pointing to the left. In other words, very, very small amounts are going to dissociate into that anion and release a proton. Only very small amounts. That means they're very, very slight dissociation, very weakly acidic. The resulting base, in this case ethoxide, is in a generic sense is called an alkoxide ion. Is a very, very strong base because it has a very strong tendency to pick up a proton. So alcohols are terribly weak as acids. However, there is one notable compound that is in this chapter, and that is phenol. Phenol is the benzene ring with an OH group on it. The OL on there reminds you that it's like an alcohol in that respect. It is definitely more acidic than water, and that means that it's a better proton donor. It can release its proton and, in this sense, react with a base such as sodium hydroxide, which is a very strong base, and the result is an anion, which is now called phenoxide. So in this context, the phenol is the acid, not very strong, but just enough to react with something that's a strong base, like sodium hydroxide, and the resulting anion is its conjugate base because it could be a proton acceptor. So phenol is the exception. Phenol has detectable acidity. If you compared methanol and ethanol to water, their acidity is very weak. It's about the same as water. There's very little dissociation to release a proton and an anion. Phenol has enough acidity that you can notice it, and there is some forward reaction, and it can react with a base. So the others will not, because they are very lousy as acids. All right, so these oxide ions are not names you're not really going to worry about, but you're going to recognize something similar coming up when we talk about ethers. So generalizations, and this will make more sense by the time the next class period has elapsed. Alcohols are going to be very, very weak acids with neutral water solutions. In other words, if you stick a piece of litmus paper in there, it'll show up neutral. And the common alcohols in their properties are flammable. Surprise, things like ethanol, methanol, propanol, they're all flammable, and they can be toxic. Some of them are definitely not to be ingested. There's two major reactions for alcohols, and those are the dehydration and oxidation reactions, which will be covered in a different class period, not in this recording. So keep track of those two things. They're flammable and definitely toxic. In other words, methanol you cannot ingest, it's poisonous. Ethanol only in moderation. All right, so some of you may remember this from children's books. My kids read this book when they were young. Curious George makes fun stories. And here's a case of chemistry in action. So there's an ether bottle. George was very curious. It smelled funny. Suddenly his head began to turn. Then he felt as if he were flying. Then rings and stars danced before his eyes. Then everything went dark. And there it is, ether. So this, from 1947, is an example of how ethers have historically been used in a way of use as anesthesia. Well, we'll talk about why that may or may not be the case so much now. It's not. Ethers are the other one of the other compounds in this chapter that have oxygens in them, and their distinguishing features and names we need to discuss. The common names for ethers are going to use the names of the two R groups, in other words, the carbon groups on that ether oxygen, and followed by the last name of ether. And you already saw some examples of this in your guided inquiry book when we were looking at boiling points and for different molecular weight compounds the other day. Flip back to that and take a look. So diethyl ether is what it sounds like. There's two ethyl groups on one oxygen. Notice that in all of these compounds, the oxygen is still going to have two lone pairs, and that gives it a geometry that is not linear, but a bent geometry. So dimethyl ether on the far left, diethyl ether on the far right, and ethyl methyl ether in between. Well, guess why this one comes first? You're going to put ethyl in front of methyl because of alphabetical order. Do not worry about trying to memorize melting points, boiling points. That's not the point. So if you were in class, we would ask you to do this together in groups so that you could challenge yourselves a little bit. So instead of doing that, I will talk you through them here. The first example, and these are on the handout that's posted on Blackboard for your real convenience to work alongside the examples that are being shown here. The first example looks like it has an oxygen in the middle with one carbon here, 3 carbons here. Methyl is the left side, propyl is the right side, alphabetical order, and you put those two together and you get a name, and it should just be methyl propyl ether. Nothing more tricky than that. The second example, we have on the left side of the oxygen a group of carbon with 2 CH3s attached. On the right side, carbon with 2 CH3s attached. Oh, there's two of the same thing. So the prefix of di will precede it, and in this case, that group, if you remember what it is, it's kind of like a Y with 3 carbons. That would be isopropyl. So this is diisopropyl ether, and yes, that looks very odd. No, not often do you see those combinations of letters together. The third one on this screen, and it's on your handout as well, look for it. Take a pause and go print out the handout if you haven't done so already. This compound, on both the two sides of the oxygen, we have two different things. Now, this turns into a piece of nomenclature that we haven't run into before. The right side is simply methyl, which is not new, but on the left side, it's a benzene ring, but it's not benzene ring as the way it's named. Instead, it's going to be described as methyl phenyl ether. Methyl will be first because it's alphabetical, and phenyl simply means this benzene ring as a substituent. People often overlook this little definition term or terminology piece, but that's how you name it in this case. There is one other way to do it, but we haven't discussed that at the moment, so let's stick with this for now. So methyl and phenyl are the two groups. All right, last example here is to dry compound, methyl and tert-butyl. This is a reminder that you're going to need to remember these alkyl groups when we get to an exam. Tert-butyl is one you don't always remember, and isopropyl is another one we have to review. But methyl and tert-butyl on an ether, so that means you're going to have one carbon on one side and a tert-butyl on the other side. And for simplicity, there you have it. So tert-butyl is when you have one carbon surrounded by 3 methyl groups for a total of 4, and that's described as tert-butyl. I hope those make sense to you. Please, by all means, let me know if you have questions. Sometimes there will be ethers that are not simply named by using the alkyl type endings on the R groups, and these will then instead be described as alkoxy groups. This is different. And so it's when you have an oxygen with that R group, and for the example here we have methoxy is methyl on an oxygen. So if you have an ether group present with some other functional group, then you have to find an alternative to naming the ether compound. The two examples on this screen show you something that requires that. In other words, this compound on the left has an alcohol and an ether, and so if we were trying to name this portion on the right with a YL ending, that's not typically done because it's an alcohol. So it doesn't make sense. Instead, this is going to be named as an alcohol with a ether substituent on it, and so this is a 2-carbon ether substituent, so it becomes much like the one above. Instead of methoxy, it will be ethoxy. And the one on the right is similar. The one on the right is described as a phenol because you've got OH group on the benzene ring, but it's methoxyphenol, and the ortho tells you where it is because you have this ether group. That's your methoxy in the ortho position on phenol. So be aware of these kinds of names for ethers. They will be coming up from time to time. If you can't name simply the R groups, the oxy kinds of names are going to help you. All right, what else do we need to know about ethers? I mentioned in class that we always want to think about names and reactions and properties, and if you recall, there are been no examples of ether reactions that you need to know because they're not particularly things that are going to react. So here it is. They're not especially reactive, so not looking for reactions there, which means they can be used for a variety of things. They're going to be used as solvents. They don't get in the way of other things, and so that's one way ethers are commonly encountered. How as in ever, what else? They are not hydrogen bonding compounds, and that gives them the lower boiling points than the alcohols. We noticed that when we were looking at the comparisons between alkanes, ethers, and alcohols recently in class, and they are a little bit polar. So I've just drawn you a simple ether, dimethyl ether, and it is somewhat polar that because of the lone pairs of electrons on the oxygen, but it can't be drawn with partial plus and partial minus the way we do for an alcohol. This gives them much lower boiling points than the alcohols, but sometimes higher boiling points than alkanes, although it depends. Sometimes they're terribly similar to the alkanes because they only have one oxygen and similar numbers of carbons otherwise. So they don't always distinguish themselves in that respect. Somewhat polar, but not the most polar compounds you're going to see more later. The other thing to notice about ethers is they're very volatile and especially flammable. There are stories of fires in Abbott Hall when a graduate student was using an ether for an experiment and something in the room sparked and the vapors of the ether caught on fire, and $10,000 of cabinet repair resulted after the call to the fire department and so forth. So yes, ethers are flammable, and you have to be careful how you use them. They are not simple because of their volatile vapor. The ability to make vapors, that's what volatility means. You cannot use them any place that flames would be present, and even sparks from electrical equipment can be dangerous. Ethers are going to be a little bit soluble or totally insoluble in water, depending on how many carbons they have. If they have too many carbons, this is a common pattern in organic chemistry. Things with too many carbons will just plain not be dissolved in water. And so most ethers past the simplest one, in other words, dimethyl ether, which turns out to be soluble. Most ethers are only going to be slightly soluble at best and not especially soluble in water. But instead, that's why they are going to be used as solvents for a variety of organic reactions because they don't get in the way due to their absence of reactivity. Not a whole lot of reactivity. The only exception to that is that if they have been open to the air and they have been left for a while, they can form very explosive compounds called peroxides. And there were tales in the 70s of stockrooms having to detonate old bottles of ethers because they were potential explosion hazards. So those things are no longer, they don't store well, that's for sure. And we try to avoid their exposures to air for those kinds of reasons. So ethers are not particularly reactive, and they are definitely flammable. So don't overlook that. And sometimes they're soluble in water, but not in general. They're good solvents. Now, we need to come back to our summaries of the properties for the different types of compounds. And this is something we don't always pay attention to closely, but let's give it a shot. Compounds are going to be soluble in water when their intermolecular forces are similar to those in water. So if they're soluble in water, they have to have dipole-dipole interactions, hydrogen bonding, or both. And the more similar the forces are to those for water, the greater the water solubility. Let's take a look at the compounds that we have encountered so far. All right, so alkanes, do they have any hydrogen bonding? Nope. Do they have dipole-dipole interactions? No, they only have London forces. Oh, by the way, are there any compounds that don't have London forces? If you remember carefully, they all have London forces. Okay, so that's what they all have in common. The alcohols we talked about already. Let's go back to that one in this list. And they are the ones that have hydrogen bonding, and that gives them much higher boiling points and better water solubility. If you ever have hydrogen bonding, that means there's also dipole-dipole interactions present. What about the ethers? The ethers do not have hydrogen bonding. There is no OH present. You have to have the OH present, such as in alcohols, or NH, we'll come to that later, as in amines. And for those compounds, hydrogen bonding is present. The alcohols and amines have it, the ethers do not. Do they have dipole interactions? Only if you can draw a partial minus and a partial plus on a bond, then you can call it dipole-dipole interactions. So ethers don't even have that. And so they don't have dipole-dipole. All they have is London forces. They have only slight polarity. And this means that they're not going to have the greatest of water solubility. Alkanes, no hydrogen bonding, no dipole-dipole interactions. Okay. So dipole-dipole interactions only occur where you can have polar bonds labeled with partial plus and partial minus. We'll work with this more and more in various contexts with other functional groups as we go along. Now, what else do you want to know about ethers? Just briefly here, they have been used as suggested by the Curious George cartoon in inhaled anesthetics, but because of their flammability hazards, there are now derivatives and alternatives to the simplest ethers that are halogenated compounds, and that's the point about halogenated compounds. They are less flammable, interestingly. And so these compounds are much safer as inhaled anesthetics. There are other funky compounds that are in flavorings, who knew, and in an insect hormone, oh well. Various kinds of ether possibilities are out there, most of which are just interesting trivia at the moment. And in case you were wondering about inhaled anesthetics, yes, they used ethers for anesthetics in original context, and that's where you might have an ether bunny. The other way of thinking about an ether bunny is if you got your oxygen between two carbons, well, that would be an ether, and it could be a bunny. Never know. So, silly chemistry jokes. There are some cyclic ethers of which you do not have to be too concerned, but one of them is just like a carbohydrate structure, and this is on your handout too, that's on the cover of your guided inquiry book. So take a look at this one and see if you can notice that in the compound on the structure of the cover of the book. The last part of this chapter is that I'm going to put in this recording is about thiols and disulfides. These are the compounds that are famous for being present in things like garlic and onions. Take a look at that picture there. Things that you've got to be careful with because they're going to be offensive to your nose. And they are literally sulfur analogs of alcohols. Why? Because sulfur and oxygen are both group 6A or 16 elements. They have 6 valence electrons. They make similar kinds of compounds. And you like patterns, and the patterns help us. So if you can make an OH, you can make an SH with similar kinds of geometries and bonding. These compounds have names that end in this word here, thiol. Thiol, the T-H-I-O, refers to sulfur in this case. And you add that to a parent compound name. So a couple simple examples here. Methane thiol is kind of what it sounds like. 1 carbon with an SH group, or ethane thiol is 2 carbons with an SH group. We will not spend a lot of time naming these, but you might as well take a look at a couple and notice that they don't seem too tricky. Ethane thiol is shown in the ball and stick diagram there at the top. These other 2 compounds are for particularly skunky odors. Skunks are known for their thiols. Whew. And they're going to be things like 2-butene 1-thiol. Isn't that a funny compound? So there's 1, 2, 3, 4, and this would be carbon 2 where the double bond is. And then the other one on the top is 3-methyl-1-butane thiol. So you're telling us the 1 is where the thiol is. 1, 2, 3, 4, and carbon 3 has a methyl group. The names kind of make sense when you get used to them. What else do you need to know about thiols? Names, reactions, and properties. Okay, we looked at a few names. I will really not emphasize them a lot, so do not distress. But properties and a couple one particular reaction we need to know. Properties, they stink, you bet. And they are going to boil at lower temperatures than alcohols with the same number of carbons. Because why? Why do they boil at lower temperatures? Well, the things that we've seen so far that have the highest boiling points were alcohols. And compared to alkanes and ethers, they had higher boiling points due to the presence of hydrogen bonding. Well, thiols are different. They do not have hydrogen bonding. And so these compounds are going to have much lower boiling points compared to similar alcohols with the same number of carbons. They just plain stink. The odors of natural gas are provided by things that are thiol compounds, low molecular weight compounds that mix with methane that allow you to detect it when there might be a leak. The one specific reaction that you do need to know is that these things will react to make what's called a disulfide in an oxidation reaction. Oxidation is suggested by O in brackets like we have here, and it always takes two. It's always going to take two sulfurs to do this because you're going to make a disulfide. So you always have to assume there's a test tube full of something, or at least more than one in reach, to put two of them together, where you're going to lose two hydrogens one off of each sulfur of the thiols, connect the sulfurs into what's called the disulfide. So the disulfide is exactly what it kind of suggests, is two sulfurs together connecting some carbons that way. This is an oxidation reaction. Oxidation is always the reverse of reduction. And so if you can take it apart by adding a reducing agent that provides hydrogens and returns back to what we call a thiol. We don't need to worry about that in great detail, but you're going to recognize oxidation and reduction as reverses of one another from time to time. Okay, so let's look at some examples of this reaction. Predict the product of this oxidation. This is a typical kind of example with thiols, and you're going to look at this and wonder what to do. Well, you have to remember that O in brackets just means we're going to oxidize. There's a variety of oxidizing agents. Even air can do it in some cases. And it's not specific to any particular oxidizer, so we just put O in a bracket. And oxidation means we're going to lose two hydrogens. Let me go back to that other slide. Think back to this one here. We're going to lose two hydrogens in the simplest case of oxidation, and the same thing is going to be the case for this thiol oxidation in this example. And so losing two hydrogens, well, if you're losing two off of sulfur compounds, remember there has to be two of these for that to happen. It's not going to be just one molecule by itself. There has to be a second one. And so in order to do that, let's put one thiol compound here. There's another thiol compound. And think about losing their two thiol hydrogens. And when they react with the oxidizer, you end up with this disulfide. Do you have to name it? No, but I would totally guess you could believe me if that would be named dipropyl disulfide. Not so tricky when you think about it, but literally you've doubled the number of carbons that are all connected by putting the two sulfurs together. Okay, that was sort of simple. Let's try another one. And, oh, I put the ball in here where you could see them. How about that? All right, so the compound at the top is drawn in the ball and stick format, which makes you frustrated at times. I get that. So remember that if you're going to oxidize it, there's going to be two. And so I redrew it with atoms drawn out. The hydrogens on the sulfurs are going to be lost in the oxidation process to make the disulfide. Where do the hydrogens go? Well, they're absorbed by the oxidizer. We don't really have to specify that. It's not the point here. It's not a big deal. That's not the emphasis in these reactions. So there we have the oxidizer creating a disulfide. No, you don't want to name that one. That one looks a little bit too complicated. No problem. That's not going to be an emphasis. Just being able to recognize how disulfides result from oxidizing thiols. Who cares? Well, when we get to proteins sometime later in chapter 18, we'll recognize that there's a particular amino acid that is important in the thiol conversation because it has one of those in its structure. It has a lot to do with three-dimensional structure of proteins, and that's going to be a lot of conversation when we get to that topic. So if you can picture this squiggly blue line at the bottom of the screen as having two thiols from a cysteine somewhere, the squiggly blue line is a protein. And the protein is going to have this thiol exposed where it can react. And so if you oxidize it sufficiently, you can make a loop. So it's going to make loops and bridges in proteins by connecting two sulfurs within a protein chain. So I realize there's an exam coming up. I hope that before the exam you're standing, and maybe after the exam you're going to think you're dying. Well, let's say that doesn't have to be the case. Good luck with your studying. I hope you use your time well. Please ask lots of questions, and I'll see you in class.